phones are turning humans into real-life cyborgs. This is even playing out in the legal realm. In the 2014 case, Riley versus California, the Supreme Court declared it unconstitutional to search and seize the digital contents of a cell phone during arrests without a warrant. The fact that the case made it all the way to the Supreme Court says a lot. It shows just how much the lower courts considered cell phones as actual physical extensions of the body. Chief Justice John Roberts highlights exactly this inclination in a memorable line from his final written opinion. These cases require us to decide how the search incident to arrest doctrine applies to modern cell phones, which are now such a pervasive and insistent part of daily life that the proverbial visitor from Mars might conclude they were an important feature of human anatomy. And with the promise of wearable technology like Google Glass, the lines are bound to get even blurrier. Have you ever heard of Thad Starner? Kind of sounds like a superhero, and I guess he sort of is one. Starner is a professor of computer science at Georgia Tech, who was one of the first people to make and use wearable computers. When Starner was a graduate student at MIT, he stopped using a desktop computer for good. In its place, he strapped on a smaller computer to his hip, put on a monocle that served as his monitor, and carried a handheld device that he called the Twiddler to input data. As the origin story goes, he was so connected to this technology at MIT that his PhD committee had to decide whether or not he could wear this gear during his oral qualifying exams. In the end, they gave him the green light, and he's been wearing a version of it ever since. Now, if this seems like cheating to you, you might want to ask yourself some questions. Is wearing regular glasses cheating for a baseball player? What about a marathon runner glancing at her watch? Or how about a student using a calculator on a physics exam? And was it cheating in my dissertation defense when I used PowerPoint slides? Or what about when I jotted down notes on a notepad? Did those give me an unfair advantage? By the way, remember Richard Feynman, the Nobel Prize-winning physicist? He used to say that he literally thought with his notebooks. There's even a method of learning called the Feynman notebook technique. Fact is, we've been expanding and enhancing our mind with external devices for ages. It's what humans do. It's so natural to think outside our own heads that philosophers have even come up with a name for it. Andy Clark and David Chalmers have dubbed it the extended mind. Clark developed this idea in his 1996 book, whose title fits in perfectly with this course. Being there, putting brain, body, and world together again. Actually, our definition of the mind owes a lot to this book. Clark's book does a couple of things relevant to our course. One, as we've done, it dispels the view that the mind is reducible to the brain. And two, it makes the case that because our minds evolved in brains housed in physical bodies navigating particular environments, the only way to understand the mind is to return it to its natural habitat. There's a lot of familiar stuff there, and we've already talked a lot about embodiment. So at this point, I'll just focus on the mesh between bodies and the physical environment. Clark challenges the traditional notion that our minds produce fully formed thoughts that then prompt actions on the environment. Clark points out that thoughts often emerge from actions on the environment. Here's a great example. The game of Scrabble requires a lot of thought. With 7 letters and an ever-changing board of more and more letters, there are just so many ways to make a move. To handle all this complexity, good players quickly learn the following strategy. Rather than imagining different words just while looking at your 7 tiles, the smartest maneuver is to physically rearrange your tiles over and over to see what words pop out. In fact, in computer Scrabble, you can even press a button called Shuffle that'll do this for you. Why would you do this when you have a perfectly good brain that can also perform such a function? Simply put, it's a hell of a lot easier. In fact, offloading work to the environment is not only easier, but more efficient and effective too. Clark argues that our cognition has been doing this sort of offloading for so long that it's become part of how humans think. I encourage you to find examples of this sort of offloading on your own. If you keep your eyes open, you'll see it everywhere. Here are 2 places to get you started. First, play the game Tetris and pay attention to how you use the rotate button. And second, check out the film Memento. The main character is an anterior-grade amnestic named Leonard who has a very creative way of remembering what he wants to remember. It's in this context that we should think about language. Clark and Chalmers and many others view language as the ultimate tool for the extended mind. Remember, just because your brain is encased in your skull doesn't mean language is too. Language is distributed among its many users, allowing them to cooperatively interpret, navigate, and act on the world. We've already talked about evolutionary mechanisms for language, so now let's finish by considering its functions in this context. What does capital L language do for the extended mind in the present? There's so many possible things to explore, but I'll leave you with just 5. For each, I'll discuss not only their benefits, but also their downsides. Let's not forget, even if language is essential to what makes us human, that doesn't mean it's always a good thing. Let's start with math. It's pretty easy to see the conceptual links between language and computer programming, and you certainly don't need a long lecture on how computers have transformed modern life. But the connection to mathematics may be less clear. Some people think about math and language as totally separate things. As a professor, I've heard literature majors tell me that they're just not math people, and math majors tell me that they're just not language people. Or consider what a bona fide mathematical genius has to say. Here's Albert Einstein. Words, as they are written or spoken, do not seem to play any role in my mechanism of thought. The psychological entities which seem to serve as elements in thought are certain signs and more or less clear images which can be voluntarily reproduced and combined. No offense to Einstein, but the truth is that mathematics is deeply grounded in language. Remember the cognitive neuroscientist Stanislaus Dehaene? Not only does he study reading, but he's an expert on math too. And that's no coincidence. In the mid-1990s, Dehaene published a book called The Number Sense, in which he explained that humans have 2 main mechanisms for mathematical ability. The first mechanism, called the approximate system, is an innate domain general skill that comes as standard equipment for human infants and is even shared across many other species. The system can make basic numeric distinctions in an approximate fashion without doing formal counting. For example, newborn babies can visually distinguish 1 item from 2, and adults can differentiate briefly flashed larger quantities of items like 50 versus 60 dots on a computer screen. And this is different from the second mechanism called the exact system, which is unique to humans starting at about age 3. The exact system uses symbolic processing to understand numbers. For example, only humans can differentiate 59 dots from 60 dots because only a human can count that high. Now, if this second mechanism sounds familiar to you, it's because it taps into the symbolic property of language. Einstein mentioned playing with signs in his head, but isn't a sign just a mathematical word for an arbitrary symbol? And aren't numbers and other notations in math just symbols too? Given this, it's no surprise that math and language are thoroughly connected in the brain. Using functional neuroimaging, Dehaene and others have shown that when you solve basic math equations, many parts of the brain's language network are activated. And disrupting that network with neurostimulation disrupts your ability to do that math. This disruption is most extreme in cases of aphasia. Often, aphasics lose the ability to do even basic arithmetic, but their ability to do approximate estimation remains. So they wouldn't know that 2 plus 2 equals 4, but they could tell you that 4 dots is more than 2 dots. As the tool that makes other tools, language has produced math, and now math has changed the way we see the world. Galileo famously said that nature's great book is written in the language of mathematics. But how far should we go with this? How does mathematics of nature help humankind appreciate nature and take care of it any better? And what would a mathematical theory reducing humans to complex equations do for us? Would it help us know who we are and how to live a good life? Would it allow us to be kinder to one another? Would it give us a sense of meaning and purpose? And what about all the scientific and technological feats enabled by math? Should we celebrate and embrace them all? Is it wise to trust artificial intelligence? Are we comfortable stockpiling weapons that can destroy us? What do we think about editing genes to build better babies? I don't have answers to these hard questions, but humans must reap what their mathematical minds have sown, and these are just a few of the big things we're left to ponder. A second major product of language, with a close relation to mathematical thought, is the capacity for logic. Logic is the cornerstone of Enlightenment thinking, and just like math, it's firmly grounded in the symbolic properties of language. And what's not to love about logic? It's like a butterfly. It's kind of hard to think of many negative things about it. Caterpillars are a different story. But is logic always a good thing? Take the poster child for logic in 1921, a young Ludwig Wittgenstein. Early in his life, Wittgenstein embraced a view that came to be known as logical positivism, which held that if you can't use a logical analysis to solve a philosophical problem, it's not worth solving. However, later in life, Wittgenstein started to see the dangers of logic. By the way, I always pay extra attention when brilliant thinkers change their minds. Here's a quote from 1953 in Wittgenstein's posthumously published Philosophical Investigations. "Philosophy is a battle against the bewitchment of our intelligence by means of language." This quote is classic Wittgenstein, full of nuance and double meaning. Here's my read. When it comes to human thought, language is both a disease and the cure. On one hand, philosophers can use everyday language, as we're using now, to identify and investigate important philosophical problems. But on the other hand, we can be misled by logical propositions of language, like if X, then Y. Wittgenstein came to believe that these propositions can create pseudo-problems and provide answers to questions that have no basis in reality. That's what philosophy must fight against. Now, this is all pretty abstract, so let's consider something much more concrete. For millennia, Eastern philosophy has also been suspicious of the beguiling effects of logic and language. Back in